Okay, next, I'm just going to do a quick demonstration of where a generator excels. So a classic example is working with Fibonacci numbers. If you're not familiar with the Fibonacci sequence, I can write out the first few. What do we have here? 2, 3, 5, 8, 13. Okay, so yeah, it always starts with 1 and 1, I believe. And you basically, to get the next number in the sequence, you add together the previous two. So 1 and 1 gives us 2. 2 and 1 gives us 3. 3 and 2 is 5. 5 and 3, 8. 8 and 5, 13. Keep going. These numbers grow pretty quickly. And to keep calculating them, we could use a regular old function. Let's say I want to generate the first 1 million was the example. Or actually, what do I have down here? What is this? Count my zeros. Yeah, this is a million. I want to get the first 1 million without using a generator or any iterator. It doesn't have to be a generator, but without using anything, just using a regular function, I would need to put them in a list. Here I have a list called nums. I have two variables, a is 0, b is 1. And then, I guess the first number is 0 in the sequence. Oh well. And then while the length of that list is less than the max, so while there are less than 1 million numbers in the list, we're going to append b. So we'll start by adding 1. And then we're going to swap the numbers. So a is now equal to b. So a is now 1. And then b is equal to a plus b, which is 0 plus 1, which is 1. But next time around, it now adds a and b together to get 2, and then keeps going and keeps going. So hopefully you can see how this works. If not, it's not necessarily the focus of this video anyway. But just to show you that it does work, we could do something like print fib list of 10. And this will give us 10 numbers. So it's not up to 10, like the highest Fibonacci number below 10. It is a 10th number in the sequence. And if we run it, okay, so there we go. We're getting the data back. It's in a list. We don't really have any other option if we're using a regular old function, because we have to keep track of what came before. And to get to the millionth Fibonacci number, we have to have every number before that one. So the list starts to grow really, really long. And if I were to do something like 1 million, we don't even have to print it. Let's just say I want to generate it. Count my zeros again. All right, here's 1 million. So this will give me the first 1 million Fibonacci numbers. I'm going to run it, and then I'm going to cut over to my computer's activity monitor on my Mac, and we'll take a look at how much memory is being used. Okay, I started it. Now I did a search for Python over here in my activity monitor. If we open it up, we can see, what's it saying? Real memory size, 503 megabytes. Okay, and I think I'm going to stop this process because my computer's not very happy when I'm recording a video and running a script like this. So I'm going to stop it, but 490 megabytes, a big number, you can see. And that's just the real memory size, but let's just focus on that. Okay, now down here, I have a generator that does the same thing in that it generates the Fibonacci sequence. But all that it does, so we have x and y instead of a and b, start at 0 and 1, and then I have a count. Instead of using the length of the list, there is no list with the generator, so it's just a counter, starts at 0. While the counter is less than the max, while it's less than a million, each time through we add 1 to count. And then all we do is the exact same thing, where we have x and y, and we assign the value of y to x, and then we update y to be x plus y. And then we yield x. And so if we did something simple, like for n in fib gen for 10, if we print n, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First 10 Fibonacci numbers. Okay, so the difference, of course, just like our last video, they're not in a list. We're just getting one at a time, and it's not storing however many in a list at the same time. If I'm trying to get the millionth Fibonacci number, it's not storing all 999,999 numbers before it, and we're just getting the current one. So if I do this instead, let's see, I think I need another 0. There we go, 1 million using the Fibonacci generator instead of the list. I run it, cut to my activity monitor, take a look. 6.7 megabytes. Serious, very drastic difference. 6.7 compared to however many 100 megabytes it was for the list version. And I'm actually printing it here as well. So In the other example, I wasn't, although that shouldn't have a massive difference on memory. It should more be about time. But anyway, that's kind of a cool example. This looks cool, but I'm worried about having a seizure. Hopefully my point here is clear. So the point is not that lists are slower, because oftentimes using a generator actually will be slower than the alternative. But instead, a generator is easier on memory, especially if you're dealing with really large sequences or things that if you stored in a list, the list would grow massive. And when I say big, I'm not talking about 1,000 or a couple thousand results. I'm talking hundreds of thousands or millions of data points. Things grow really, really large when you use lists. But if you instead use a generator, the difference can be significant. Again, not in time necessarily, but in memory. Okay, that wraps this up. The last thing about generators I'll show you is called generator expressions. Quick and easy. See you then.